Hi, I'm Peter Taylor. I'm a postdoc at CCAP at the Ohio State University. And today I'm going to be talking about how we can perform unsupervised machine learning searches for symmetry violations in the universe, and in particular, parity violation in spectroscopic galaxy maps. And all this work is with my collaborators, Matthew Craigie, Carol Cuesta, and Jan Senting. Okay, so to keep it simple, to start out with, let's just imagine that the universe is a 2D sheet and that we have galaxies on this 2D sheet. Now, every triplet of galaxies define a triangle, and in particular, you can imagine that those galaxies lie at the vertexes of a triangle. So what we can do is we can ask, are there more left than right-handed triangles? And if the answer to that question is yes, or there's more uh, right than left-handed triangles, up to our statistical uncertainties, then that tells us that there is mirror asymmetry in this universe. And that's because you can never take a left-handed triangle and then rotate it or translate it into a right-handed triangle in 2D. Okay, but of course, the universe is actually 3D. So now, rather than looking at mirror asymmetries, we're looking for what's called parity violations. So we're asking, does the universe look the same if we take each point X, Y, and Z and reflect about a point to another point minus X, minus Y, and minus Z? But now, if we're looking for these parity violations, we can no longer use triplets of galaxies. And that's because if I have a left-handed triangle and a right-handed triangle, if I were to look at that right-handed triangle from the other side in 3D, it would look like a left-handed triangle. So if I want to learn about parity violation, then I have to look at tetrahedra and ask, do I have more left or right-handed tetrahedra? Because there's no way in 3D that I can rotate or translate one of these left-handed tetrahedra into a right-handed tetrahedra. So if you like, what we're doing here is really looking at the 4-point correlation function for spectroscopic galaxy surveys. So the reason that this is an interesting thing to think about now is just in the last couple of years, there have been two possible detections. So we have this 2.9 sigma detection by Oliver Philcox on the left, nearly 3 sigma. And then we have this 7.1 sigma detection by Jiamin Hu and collaborators here on the right. And what this massive data points is really showing, so each one of these data points corresponds to a particular tetrahedral configuration up to rotation. So if that data point lies above the line, then that means that we have more right than left-handed tetrahedra. And if it lies below, then we have more left than right. And then these error bars are either estimated from theory, or potentially in the future, they could also be estimated from simulations. So then really the question they're asking is, are these data points consistent with zero, given these estimated uncertainties? And the answer here seems to be no. Okay, so what's the interpretation here? Well, I think the thing that people usually jump to is you think, okay, maybe this is just observational systematics. But actually, I think this is really quite unlikely, because to get parity violation, you do actually need some coupling between the systematics perpendicular to the line of sight and radial to the line of sight. And it's really unclear how this could actually happen. The second possibility, the most exciting one, is that this is new physics. So there's nothing in our standard model of cosmology that predicts parity violation. So this could potentially be hints about the epoch of inflation. And there's already many models, inflationary models, that predict parity violation. But the third possibility is that we're just underestimating our uncertainties. So that really the signal that we detect is actually statistically consistent with no parity violation. And that's partially the topic of this talk today. Right. So what are the problems with this 4-point analysis? So the first of these is the uncertainty quantification, right? So these error bars, or the way we quantify the uncertainty, really either comes from theory, from analytic theory, or from simulations. And neither theory or simulations completely captures the real uncertainties in real data. So if we were to make, for example, these error bars, say 30% larger, this detection of parity violation would go away. And indeed, in a recent paper, Oliver showed that in his 2.9 sigma detection, changing the suite of simulations that we use to quantify the uncertainty make that result go away. So the other problem with the four-point analysis, of course, is that we only get information from tetrahedra. But actually, any polygon with more than n sides is going to be giving us information about parity. So by just doing the four-point analysis, we're potentially leaving a huge amount of information on the table. And this might cause us to miss parity violating signals in the future, even if they're really there and physical. So with my collaborators, we've proposed a new approach, which was originally proposed by Christopher Lester, to look for parity violations in the Large Hadron Collider. And the way this approach works is you have this, this huge 3D volume, which is your spectroscopic survey. And then what you do is you divide that volume up into little chunks. So I'll call each one of these chunks X, and then for each of those chunks, you can take the parity flipped image or parity flipped galaxy map P of X. So in these plots here, that if you like, the colors or the intensities represent the number of galaxies in each pixel. And then what you do is you take some of the chunks, you call that a training set, and then you take some of the chunks or pairs of chunks and parity flip chunks, and you leave that aside for later to actually make the detection. Okay, so then you go back to the training set. So you've got each of these pairs X and P of X, and then you feed these through some neural network G. And there's a huge amount of choice about what this neural network could be. In today's talk, it's just going to be a convolutional neural network in 3D or 2D. And then what you do is you train this network to maximize the difference between G of X and GP of X. And I'll call that F. So the reason that this is a sensible thing to do is that once the network is trained, then you go away and you show it your validation set, that set of data that you left aside to actually make the detection. Now, in that data, X and its parity flipped version of that data, P of X, are equally likely if there's no parity violations present in the real universe. So what that means is that the average value of F over this detection set should be 0. But if you find that the average value of F is larger than 0, then that tells us that you have parity violation in the data. Okay, so how do we quantify the uncertainties? Well, with that detection set that we've left aside, we do a bootstrap resampling of all the chunks, recompute the average value of F, and then repeat. So we get some distribution on the average value of F, which allows us to quantify our uncertainties. Okay, so does this method actually work? So we did a test in 2D using convolutional neural networks. So here we're looking for mirror asymmetry rather than parity violations, but the same idea works in 3D. So on the left, what I've done is I've taken a bunch of left-handed triangles and right-handed triangles. I've allowed them to rotate around randomly and allow them to translate around the field. And I do this 10,000 times. So the intensity here on the left, or the colors, tell you the number of galaxies in each pixel. So I generate 10,000 of these maps. And I've done this in such a way that on average, there are an equal number of left and right-handed triangles. And then on the right, I do exactly the same thing. generate 10,000 of these things. But I've done it in such a way that on average, there is a slightly less than 1% overabundance of left versus right-handed triangles. So absolutely tiny amount of mirror asymmetry. And then I've gone away and tried to detect mirror asymmetry using the technique described on the last slide. Right, so on the left, what I'm showing is the distribution of the average value of f over the detection set when there's no mirror asymmetry present in the data. And that distribution is consistent with 0, this dotted line. So that's great. So we haven't detected any mirror asymmetry when it isn't there. But then on the right, I repeat the same procedure, but this time I look at the set of data where there's this tiny overabundance of left versus right-handed triangle. And here you can see that this distribution on the average value of f is shifted to the right of 0. So we detect this mirror asymmetry at really high confidence. So what we're doing now is extending these techniques to 3D. This is proving to be a really challenging problem, but my collaborators and myself are kind of tackling this using several different architectures, and we hope that in the very near future we should be able to make detections on realistic data in 3D. And so I think I'll just leave it here. So again, the ultimate goal is that we want to be able to detect parity violation without having to rely on simulations or theory to quantify the uncertainties. Because there's a decent chance at the moment that the signal that we're seeing is actually due to underestimating our error bars. At the same time, we also want to be able to extract parity information from beyond the 4-point function, because at the moment we're potentially leaving a huge amount of signal on the table. And right now, we are working on extending this to 3D. And a particularly promising approach, I wanted to highlight this paper by Matt Craigie that's come out just in the last couple of weeks, where rather than using CNNs, we use a new technique called neural fields. And we've shown that in 2D, this dramatically outperforms a CNN architecture. And we're now working on extending this to the 3D case, and then eventually to trying out this method on real data. And I think I'll leave it there. Thanks very much for listening.